Hello and welcome to our second lecture, Algebra of Sets Part 2. I hope you remember the definition of algebra of a set and certain proportions that we have discussed in our last lecture. We'll start this as a continuation. So the proposition reads. Before we read the proposition, let me say that we'll not be calling script A this notion all the time as script A. At times, I'll be calling it as A when there arises no confusion. If you see only script and the whole slide, then I'll simply say A, B, and so on, and you'll understand. If there are both this collection of subsets and sets as well, then I'll say script A and simply A. Okay, so the proposition reads, let script A be an algebra of subsets of X and AI is a sequence of sets in A. Then there exists a sequence BI of sets in script A such that Bm intersection Bn is empty whenever m is not equal to n. And interestingly, union of Bi is equals to Ai. So given a sequence, we are interested in finding out a sequence of these joint sets. And we are not compromising anywhere because union will remain the same. Well, the result is trivial when Ai, the sequence is finite. So I want you to verify the statement and define what you mean by sequence is finite. So without loss of generality, we will assume that the sequence is in infinite sequence. Well, if AI is the original sequence are disjoint in nature, then we have nothing to prove. So not disjoint. We set b1 equal to a1, and for each positive integer n greater than 1, we can define this bn as this an minus union of all ai's up to an minus 1. And this can be written as in terms of complements. An intersection a1 complement and so on up to an minus 1 complement. Now, since script A is an algebra, AIs are subsets in that algebra, so their complement and hence their union also in script A, so Bn are in script A, and by definition Bn is a subset of An for each n. Now, for any two sets Bn and Bm, we assume that m is strictly less than n. We know Bm is a subset of Am, and then its intersection Bm intersection Bn would be subset of Am intersection Bn. Now Bn by definition will include this Am complement. So in the intersection they will give empty. That means Bm intersection Bn is an empty set whenever m not equals to n. Remember we have started with m strictly less than n. So, but we have said that this result holds whenever m not equals to n. Why? Well, if m not equal to n, either this is true or the reverse. So you can work it out, right? And since Bi is a subset of Ais, this is trivial. On the other hand, if X is any element in this union, then X would be one of these Ais. But that means that if we can always find n to be the smallest value of I for which X belongs to Ai, that means all the previous entries A1, A2 up to An minus 1 will not hold X, but X will be in An and onward. That means X belongs to An intersection all these complements. In other words, X belongs to Bn. Started with X in this union, and we have found that X belongs to Bn for some n. That means this union is subset of union of B's. From the previous result, if we combine, we get the equality. Well, now we come to the definition of sigma algebra, which we need, in fact. An algebra script A of sets is called the sigma algebra or Borel field if every union of a countable sets class of sets in script A is again in script A. In other words, if AI is a sequence of sets, then their union is also in script A. Algebra, we have finite union. Sigma algebra, we have countable union. Interestingly, In view of De Morgan's law, intersection of countable class of sets, sigma algebra script A is also in script A. So sigma algebra not only closed under countable union, it's closed under countable intersection in view of De Morgan's law and in view of the first property that if a set A belongs to script A, its complement will also belong to script A. Well, the definition says every sigma algebra is an algebra, not the converse. So first try to prove it. The converse, think about it. It may take some time. We'll come back to it. This proposition is similar to a previous proposition. If you remember, we start with a collection of subsets of X. Let's call it script C. Then there is a smallest sigma algebra containing script C. That means there is a sigma algebra script A containing script C, such that if there is just under sigma algebra script B containing C, then A would be a subset of script B. A would be smaller. The proof exactly the same. So we'll get 5 marks for the proof. The smallest sigma algebra containing script C is called the sigma algebra generated by C as earlier. Remember similarity. In algebra also we have the same definition. In sigma algebra also this holds. Let's try certain problems. So we have a sigma algebra and then a subset Y. So we like to reconstruct a new collection in such a way that if A belongs to this sigma algebra script A, then collect all the subsets of the form A subset intersection Y. We'll name it script AY and we'll show that script AY is a sigma algebra subsets of B. This now changed to subsets of. Well, script A is non-empty, Y non-empty. Assume otherwise, that's a trivial result. Y is not also equals to X, otherwise you have no distinction between script A and script AY. So hence AY is non-empty. By definition, all the members are subsets of Y. So any algebra you get out of it would be algebra of subsets of Y. Consider any element B. In script AY, it will be obviously of the form A intersection Y, where A is a subset. And then if you take complement, then you'll find that B complement is in script AY. The point to remember is that we are looking for complement in Y, not in X, and hence we have this reread it. Well, once this is done, next step is easy. And if we need to show that it's closed under countable union. So take a countable sets like a sequence bi in AY. Bi is of the forms AI intersection Y. Then union of bi will obviously be in script AY because of this fact that union of AI is in A. And hence script AY is a sigma algebra of subsets of Y. Remember that, of Y. Well, another interesting problem, script A is the algebra generated by a collection script C. And then you have to show that script A and script C is the same sigma algebra. So let's start with two different sigma algebras, one B, one B prime, one generated by A, one generated by C. A is generated by C and B is generated by A. So obviously this inclusion holds. C is a subset of A, which is a subset of B. Now B is a sigma algebra containing C, but B prime is the smallest, so B prime would be included in B. Other way around, B prime is the sigma algebra generated by C, so B prime is an algebra containing C. Since A is the algebra generated by C, A subset of B prime and B prime now contains A, but B is the smallest sigma algebra, hence B subset of B prime. In other words, script B equals script B prime. That means we have the same sigma algebra generated by script A as well as script C. For certain problems, we like you to deal with. This is the nth algebra of sets. So the problems Does an algebra of sets closed under difference and symmetry difference? That means if A and B belongs to the algebra, then whether A minus B would again belong, and so on. Union of two algebras is also an algebra. Justify your answer. If yes, why? If no, why? And give an example of an algebra which is not in sigma algebra. Take your time. Thank you.